Hi, my name is Neal Damani and this is my lab for surrounding circuits. As an introduction, our goals are to predict the behavior of circuits containing resistors in series and in parallel, to examine the behavior of the ohmic resistors and capacitors using a p-het simulation, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. Some of our findings were that the current in the two resistor circuit was equal to 0.02 amps. The calculated values and experimental values for the current and potential difference match. The greater the resistance of a resistor in an RC circuit, the longer the time for the capacitor to charge and discharge, and our time constraint was equal to 5.984 seconds. Some of our key concepts are the node rule, that our current in is equivalent to our current out, and our loop rule, which is that the difference of potential for a round trip path is zero. These both follow the conservation of energy. Another key concept was electrical resistance, and another key concept was capacitance. Here are some of our visual models. Our system is our ammeter or our voltmeter, which is whatever device is measuring our current or potential difference. And for our surroundings, it was a circuit, so it includes current and potential difference in the circuits. For part one of our initial simple circuit, we constructed a circuit in our p-het simulation that consisted of two batteries, each 1.5 volts, two resistors, one being 47 ohms and the other 100 ohms, and two ammeters. Our predicted current was 0.0204 amps, and our actual current was 0.02 amps, and our reversed ammeter read at negative 0.02 amps. Part 2 being our open circuit, our predicted values for potential difference from the batteries was 3 volts, our current was 0 amps, and these were the same as our experimental values, meaning they agreed. For part 3, where we measure the potential differences around the circuit, our potential differences from A to B were 3 volts, B to C were 0 volts, C to D was negative 0.96 volts, D to E was 0 volts, E to F was negative 2.04 volts, F to G was 0 volts, G to H was 0 volts, and H to A was 0 volts. And given this, the findings support the loop rule because it's equivalent to 0 volts when you add the 3 minus the 0.96 and minus the 2.04. For part 4, for our ammeter in parallel, when we reconstructed the circuit so that the ammeter is in parallel with the ohm resistor, the current measured by the ammeters increased from 0.02 amps to 0.06 amps due to the parallel construction. For part 5, calculating the resistance, when we calculated the resistance of the resistors, we used R equals V over I. Our resistance for a 47 ohm resistor was 48 ohms. Our resistance for a 100 ohm resistor was 102 ohms, and for our resistance of our ammeter and our wire, they are both equal to 0 ohms. For part 6 of our RC circuit, charging and discharging times, we constructed our RC circuit with a 10 ohm resistor, a 200 mF capacitor, and a 9 volt battery. And then we measured the time to charge the capacitor and the time to discharge the capacitor, and we repeated with a 20 ohm resistor. Our results for the 10 ohm resistor had a charging time of 15.4 seconds and a discharging time of 15.2 seconds, and our 20 ohm resistor had a charging time of 25.9 seconds and a discharging time of 27.5 seconds, meaning that the greater resistance is equal to a longer time for the charges to move, and a longer time for the potential difference to decrease, as well as a longer time to reach a zero current. For part 7, the time-dependent voltage, determining the time constant of an RC circuit, we constructed an RC circuit with a 9 volt battery, 30 ohm resistor, and 2000 mF capacitor. And as we computed it, our slope is equal to negative 0.1671. Our slope is equal to negative 1 over our RC, which means that our RC value is equal to 5.984 seconds. When it comes to our discussion, if we were doing this lab in real life and using an actual ammeter instead of an ideal simulated ammeter, a real ammeter has non-zero resistance, even if it's small, and the wires have non-zero resistance. This would have resulted in a slightly decreased current in the circuit, meaning the current readings on the ammeter would decrease. And then if we were to do this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? And will this prediction happen in real life? The ideal model predicts that the capacitor would reach full charge within a second or almost instantaneously, which cannot happen in real life. Wires would have a non-zero resistance that would increase the time for the capacitor to reach our full charge, and the resistance of the capacitor would also have to be considered in real life. Thank you.